Welcome back, everyone. This is CSM Walkthroughs, week 4, and we are covering question 4, part B for this video. Okay, compared to part A, where we used a DC voltage, for part B, we're using an AC voltage input signal. And this AC input signals mean that for any output, voltage output we will still be having some sinusoidal signal with the same frequency. This is saying that this V out will be in the form of some phasor that we don't yet know, but will not be transient. Meaning it will not be dependent on time. So we will have some factor here times e to the power of j omega t. And we will have 2 here, just in case we need which is just a factor that can be changed by the definition of our phasor. Yeah, so it's not that important, but the important part is that our V out can be expressed as these 3 factors. And this factor here is only possible when we have a sinusoidal input signal. So yeah, so that's basically what this whole problem is talking about. It's showing you that for a DC input, you can't use a phasor, and for an AC input, you are allowed to and usually encouraged to use a phasor analysis. Okay, so in case you don't remember how to solve a phasor problem, I wrote out these 4 steps to solving any phasor problem. First, you convert all the input signals to a phasor form. So that would be we will have our magnitude of our input signal over 2 times e to the power of j and then phase. But notice that we don't have a cosine here. We have a sine instead. So that means we should first convert our input signal and our time domain to a cosine form. So that means, and the reason why we're doing this is because when we're using this form, I actually forgot to put something very important here, which is a real part. So we're actually solving for the real part of this exponential. And that makes sense because this exponential is actually a sum of a cosine and j times sine. So that means our the real part of this will only be looking at the cosine part. And the cosine part will have the phase that we will be using for our phasor. So this phase here should be a phase inside this cosine, but not sine. Okay, so that's why we're converting the sine signal into a cosine signal so that we can just borrow the phase part of the cosine signal. Okay, so we know that our sine for a 10,000 t plus 30 degrees is equal to cosine t plus 30 degrees minus 90 degrees. So we know that for a cosine, we have this 90 degrees phase shift. So finally, we got that our phase that we were looking for is negative 60 degrees. So that's what we are going to be using here. Yeah, so we actually don't need a tan. We just need negative 60 here, 60 degrees. And now, I think we're good to go for this step 1. Okay. Next, we have step 2, which is redraw the circuit with impedances. So you will notice here that, okay, my tablet is acting weird, but we can do this. Please. Okay. So you notice here that we have our very complicated circuit with a capacitor and 2 inductors and several resistors. So we will now simplify this and then put everything into impedances. Well, let's convert everything into impedances first and then simplify it. That sounds good. Okay, so the resistors, the impedance of the resistor is just the resistance. So we will have 2 ohms for the impedances. 2 ohms, 1 ohm, 1 ohm, and 1 ohm. For an inductor, we have j omega L as our impedance. So we will put, well, for the omega, we found out that it's 10,000. So we will just put j times 10,000 times 10 to the power of negative 4, the impedance, the inductance. So that just gives us a j. So j ohms is the impedance for the inductor. And here we have the same inductance, and it should have the same frequency throughout the circuit. So we will still have a j ohm as the impedance. Finally, we solve for the impedance of the capacitor, which is 1 over j omega c. And we use the same omega again. So we will use 10,000 for the omega. And for the capacitance, we have 10 to the power of negative 4 again. So that will give us 1 over j. We don't want j in our numerator, denominator, I mean. So we multiply by j over j, which is just 1. We know we're allowed to do that. So j squared gives us -1. So we will have -j. Okay, so we finally made everything in terms of impedances. And now we will simplify this circuit because this circuit is way too complicated for us to solve. And it's also very easy to simplify. So I will say we have one impedance, namely Z1 here, and one impedance, another impedance, which is Z2 there, and this goes to ground. And here we have V out. Let's put everything in phasor domain. Okay, good. I kind of thought of this thing because I saw something in series and parallel here, something in parallel and series here. So I thought maybe I could put them into two groups. But it doesn't matter. If you find a better way, you could use that. Okay, let's now solve for this impedance 1. Well, we see that the 2 ohms and the parallel part are in series, so we just add them. And the parallel part we use, okay. Okay. We use just the normal resistor formula. So that would be a reciprocal. So 1 over one of the impedance, which is J, plus 1 over the other impedance, 1, should be equal to the total impedance reciprocal. Yeah. So if that's confusing, let's say we have two resistors in parallel, and we want to replace this into one big resistor. We don't know it's big, but let's say it's R total. So we know that 1 over R total is equal to R1 plus R1's reciprocal plus R2 reciprocal. So I just put this into here and this into there. Wait, this is way too complicated. But yeah, basically we know that R1, RT is just the reciprocal of the sum of these two fractions. So that's what I wrote down here. Okay. So anyways, if we solve for this is pretty easy. We get 2 plus 3j over 1 plus j. Okay. And now let's solve for z2. Well, z2 is just this part and this part are both in series. So we have this resistor and the capacitor in series, and the resistor and the inductor as series. And we want to connect them in parallel. So let's first solve for the series part. So this is 1 plus -j. So that's 1 minus j and the other one is 1 plus j. So now we solve for the total impedance, which is 1 over the reciprocal of one impedance plus the reciprocal of the other. So that gives us, well, that gives us 1 over one. Okay. Yeah, if you have any questions about how I did this, just leave below in the comments or on the Piazza post, and I will try to answer as quickly as possible. But anyways, now we simplified this very complex circuit into a very simple voltage divider with the two impedances as this and that. Okay, so I will just redraw that circuit back here with our green pen because we're on step 2. We're only on step 2. Wow. Okay. So this impedance was 2 plus 3j over 1 plus j. And the impedance here was 1. And we have V out. For Vn, we solved for it. It was this one here. So 5 e to the power of j, 60 degrees. Okay. I think we're now ready for step 3. That's solving for the output here and the phasor domain. Well, we already know that this is a voltage divider. So by this point, you should know that a voltage divider, so noticing a form of voltage divider is very important in phasor analysis. So for this one, we have V out phasor is equal to the two impedances, the sum of two impedances on the denominator and 1 on the numerator. And then we multiply this by our V input phasor. So if we do this algebra, we get 1 plus j over 3 plus 4j times times 5 e to the power of negative j, 60 degrees. And now we want to multiply this by the polar form, the rectangular form by the polar form. So we probably want to convert the rectangular form into a polar form. So we first solve for the magnitude, which is just 1 squared plus the imaginary part here is 1. So like this, and the magnitude for the denominator is 3 squared plus 4 squared, and the phase for the numerator. So remember, we use a subtraction for a phasor for a complex number division. So the phase will be it's 1/1. So a tan 1/1, which is just pi over 2 minus a tan 4/3. Well, do we need a calculator for this? Fortunately, we don't yet because we are actually given. So they magically knew that we will need this calculation. So we were given that this is 51 degrees. Okay, we are using degrees here, so I will use degrees instead of pi over 2. Okay, now we solve for this. So that's square root 2 over square root, this is 16, so that's 5. And e to the power of j 39 degrees. I'm just gonna check my notes to make sure I'm doing it right. This is weird. Okay, turns out I made a mistake here. Okay, so here, a tan 1 is actually 45 degrees. That was dumb. Okay, so this is just -6 degrees. And yeah, that'd be all for the algebra of this part. So we plug this into here. Let me highlight that in same colors. And we're now ready for our calculation for the V out phasor. So we multiplied the magnitudes. I'm happy that these canceled out. And we subtract or add the phases. So that's -j66 degrees. So finally, that would be our phasor of voltage output. Okay, so we're now done with step 3 here, and I will do step 4 as a finale. Okay, for step 4, we should convert this back to the time domain because the answer is asking for a time domain specifically. They will, you need to answer in a time domain usually because the input was given in the time domain. So this step is normally required even if they don't say it in the question. So, so for the time domain, well, if you are confused, you could use this part here. It's pretty messy, but you could use the fact that it's the real part of the phasor times e to the power of j omega t. Doubled. But here we will just use our cosine. So our cosine will have omega t plus phi as a general form and our v naught as a magnitude. But we already know that our magnitude is 2 times the magnitude of our phasor, and our frequency is the same, didn't change, and our phase is -66 degrees from here. Okay, so wait. So this is our final answer for this phasor analysis problem. It's a pretty long problem because we have 4 steps to do, but it's pretty formulaic, so I'm sure you will be able to solve this as long as we don't have a difficult circuit analysis problem. Please be aware that you could always simplify these problems into simpler forms as long as you have only the impedances, like different circuit elements uh, in parallel or series. And you could also use special forms of circuits uh, such as voltage divider. Yeah, so that'd be all for part B. And for question 4, I hope that helped. And that'd be all for worksheet 3. I hope that helped, and see you next time. Bye.